All right, so this is part 2, learning unit number 5, CSTN 283-235. And so we just finished review of some basic construction assemblies, and why that's critical and why that's important is one of the biggest components that we talk about when we talk about building efficiency is the thermal envelope. And all of those different assemblies have to be combined to create the thermal envelope. The 4 basic functions of the thermal envelope, and these all have to happen simultaneously, but contain heat, handle moisture as a vapor, and we're gonna revisit that because we talked at break, and I think we'll spend a few minutes just revisiting moisture drive a little bit. So 4 functions: contain the heat, handle moisture as a vapor, keep bulk moisture out, so our bulk moisture is rain, snow, everything that's coming from the outside, and then control and contain our air movement. So the thermal envelope isn't necessarily any, as I said, it's a different sort of assembly. It's not one component. It's a series of components that combine to create that separation of the building from the inside, from the outside. And one of the most important things and the hardest things is getting that attachment and completeness of the thermal envelope. In order to control that air, in order to contain the heat, in order to contain the moisture drive, it's got to be a complete system. If you've got, and I mentioned a couple little areas where the walls and the roofs connect, where the floor connects to the framing, where the foundation connects, if you've got areas that have disconnect, and you have air, heat, moisture flowing out, it's called thermal bypass. And so the whole goal of the thermal envelope is to, as much as possible, eliminate thermal bypass. One of the things that talks about unbroken thermal envelope, in a good design in a cross section like this, and we'll talk a little bit more about design in a second, but you should be able to start at one point in the building, and if you're looking at it on paper in a context like this, you should be able to trace it with your finger, and you should be able to easily follow that path of the thermal envelope without ever lifting your finger. And if you start to have pathways in there where you have to start moving and taking a lot of 90s and jigs and jogs and all the different angles, it usually creates, when you've got connections and corners and direction changes, it creates potential problems and interruptions in the thermal envelope. So we'll talk more about design. We're going to play with some different wall assemblies when we do our res check, and we're going to start to change assemblies to see how one assembly performs better than the other. But one key concept in design is really back to the whole keep it simple principle. In a lot of the architecture that we see with a lot of different cut up features to it and different roof lines, and may be aesthetically appealing from the outside, but when it comes to actually creating a thermal envelope and creating a barrier between the inside and the outside, the more changes, the more profiles that you have to change, the harder it is to create that thermal envelope. When we talk about the pieces and the parts of the thermal envelope, we're talking about starting from the outside in, we're talking about our exterior cladding, our siding. Behind that is some sort of rain screen or weather-resistant barrier. Then we've got our sheeting, our insulation, and then finally our finish inside. And within that, we've got to have the insulation, the air barrier, and the thermal block. And they all need to be aligned, and they all need to be working together. So again, just another graphic illustration of the difference between inside and outside and what the thermal envelope does. And I want to back up a little bit. We talked at break, and there was discussion on airflow and moisture migration, and so the conductive heat loss and heat traveling through materials inside and out is one of the big ways that our buildings lose heat. The second way that our buildings lose heat significantly is through airflow, uncontrolled airflow. Holes, gaps, cracks, anywhere in the building that air can get through, we're going to have airflow. A few basic things to remember: air always flows from high pressure to low pressure. And we talked about heat, and that always flows from hot to cold. And then the other thing to talk about in that is moisture. And moisture always flows from high to low as well. So higher relative humidity to lower relative humidity. Why this becomes important and why it's so important to control the air, it isn't just as much of the heat loss, but it's also with that air there's always moisture. And whether it's coming in from the outside or whether it's going out from the inside, that moisture, if it gets into the wall cavity and reaches a certain temperature, has the potential to condensate. So as we get buildings tighter and tighter and tighter, which is the number one thing that we've been doing in energy efficiency over the last couple decades, we do cut down on the heat loss, we do cut down on the amount of airflow inside to out, but we also trap a lot of that air. And with that air that we trap, we have moisture vapor with it. You talk about the stack effect and the fact that warmer air rises. Did you spend time on that? So the basic principle, and you guys can't answer because you know this, and it's one of my pet peeves. A lot of times you'll hear people say that heat rises. The heat doesn't rise. But as air warms and it gets hotter, it will rise because it becomes less dense. When we talk about this in the context of airflow within a house, it becomes pretty important because if we're not controlling the airflow and we've got a leaky house, that natural warming of the air and that gravitational rise, the air will rise up to the higher levels of the house. If we've got a leaky house, it's going to escape. And if that conditioned air, that heated air escapes, what has to happen? It's got to be replaced, and what's it being replaced with? Unconditioned air. In an older house, this can be fairly significant. If you've got a multi-level house that's very, very leaky, you've got a heating system, it heats the air, that air warms, and as that air warms, it rises, it leaks from everywhere. And we'll go through this when we look at our thermal bypass checklist, but it leaks out of electrical outlets, it leaks out of lighting fixtures, it leaks just through connections of interior walls to the trusses, it leaks around the windows and doors, it leaks just about everywhere it possibly can. And so the warm air rises and leaks, and it's got to be replaced with other air. So it's just constantly moving, cooling down the house. The biggest part of that is with that air, you're also moving moisture vapor. It's not just air going into the walls. So holes in the building envelope don't just impact your energy efficiency, they impact how much moisture drive goes into the wall. So here's just an example of air movement and how little tiny cracks can make a significant difference. So this is over the course of a heating season. This slide has been around forever. I think I remember seeing this same slide about 25 years ago. But the physics of it hasn't changed. If you've got a well-sealed wall, and here they're just using a 4x8 sheet of drywall as an example with no holes in it, it will get moisture through it via diffusion, but it's a fairly insignificant amount. Over the course of a heating season, you're looking at 1/3 of a quart of water. In that same square footage, if you have just a 1-inch hole, one square inch hole, you'll get 30 quarts of water. So nearly 90 times the amount of moisture vapor can go through a gap or a crack in the wall. Where this is starting to become much more problematic is because we're sealing the buildings up that much tighter. And so if you have an incomplete air barrier and you're not stopping that airflow getting into the wall, you're also driving all that moisture vapor into the wall. And if that moisture vapor, if it's 70 degrees inside and it's 20 degrees outside, your relative humidity is 40% inside and 10% outside, you're going to have significant pressure pushing that air and pushing that moisture through the wall, and somewhere in the middle of that wall it's going to reach dew point. And that's where the problems begin. So this is why the thermal envelope in the building assembly is so important, and that's why the moisture drive and managing that within the thermal envelope is also significantly important. So we'll spend a little bit more time on this. Does that make sense then? Does that and just kind of rules of thumb, always remember about heat. And if you can just remember the high to low, you're going to be safe. Heat always wants to move from warmer to colder. It always wants to move from a higher temperature to a lower temperature. So depending on what your delta T is from inside to out, the greater the difference, the more that heat's going to want to conduct from inside to out. When you talk about moisture vapor, it's also from higher to lower. It's always wanting to go from higher relative humidity to lower relative humidity. Make sense? And again, you have to understand a little bit about your climate differences to understand why you can't, and going back to how complicated buildings are, which is what we started out the day with, you can't necessarily use the same assembly in the same way in every climate zone. Because when you think about the logic of that, if heat likes to go from hot to cold, moisture likes to go from high relative humidity to low relative humidity, in the winter in Montana, where's the moisture going to go from? It's going to go from in to out, because we've got warm inside, cold outside. So that's where the heat's going to want to go. We've got higher relative humidity inside and lower relative humidity outside. So that's also going, not only are we losing our heat and helping to drive that conduction and convective airflow, but we've also got the vapor drive going from high humidity to low humidity. So we have to stop it on the inside of the wall. We try to stop that air from going into the wall cavity. If we're in southern Georgia and it's 110 degrees outside and 90% relative humidity, but it's 68 degrees inside and 50% relative humidity, where's the moisture going to go? From outside to in. So if you use, in our climate, if we're using that vapor barrier and we're putting that on the inside wall to stop that moisture from getting in so it can't condense inside the wall cavity, if we use that same assembly in Georgia, what's going to happen? All that moisture is going to get in the wall and then it's going to condense on the inside. So there's an entire half a semester on heat transfer, moisture migration, and flow in 15 minutes, so I'm sure it all sunk in. So one of the things we're going to spend a significant amount of time on over the next couple weeks, and somebody asked me about the BPI shell, and I'll talk with Brad and make sure that gets up next week. Who's doing the BPI certification? So have you done anything? Have you guys met yet? What's the plan of attack on that?
Heard anything? We got an email 2 or 3 weeks ago that said Brad requested a Moodle shell for it, and it would be up the following week.
Brad did say something though that he was going to hold off till later in the semester so we get further along in this course.
I would probably think that that's a good idea, but we're going to get into. We've got one blower door. We've got a colleague of mine that's going to help us, and we'll have 2 blower doors, and hopefully everybody's going to get a chance to use the blower door on their own. But first things first, we'll learn about it. But yeah, I think after you go through this process, it'll make that BPI class. It'll make more sense, and you'll breeze right through it. So, but kind of, and this is a little bit more revisiting back into what's in the book, talking about air leakage and testing the thermal envelope. We'll spend a lot more time. We'll visit the thermal envelope again, and we'll look at different assemblies and structures. But testing the airflow and pressure in there is a significant part of what we're going to work on, and you'll all get to use the blower door. So the basic concept, and if you've all gone through and read chapters 3 and 4, you know already. Basic concept of the blower door is to create a differentiation in pressure. And by creating a differentiation in pressure, you can see how much air is going in or out of a house. Most of the time for a residential, you'll be doing, it's a single point test. As you get into larger buildings, it becomes a little more intricate, and you've got to do some multi-point tests. But we'll concentrate just on residential. We'll keep it simple. So again, basically all the blower door is doing, there's always differentiations in pressure, and again, we didn't spend too much time talking about that in the context of the building, but everything from natural atmospheric pressure to the wind to the mechanical systems, they're always creating pressure differentiations inside of a building. But they're usually not large enough to be able to measure in any capacity, so the natural air change per hour is not something that we can measure. So the blower door is used to pressurize or depressurize the structure so that it can exaggerate the pressure differentiation, so that if you have negative pressure inside the building, and we'll go over pascals in just a minute, but you create a situation that's either under-pressurized or over-pressurized in the building. You can calculate how much airflow is going in and out over a given time, and you can actually rate your building on how many air changes per hour it has. So we'll talk about the potential size of holes in the house, and we'll calculate how to do that here in just a bit. Can be done before or after air sealing, and this is where coming into building energy efficiency and energy efficiency improvements, it's a great technique for setting the baseline. So when you're coming into an existing building or an existing house, utilizing the blower door and the calculations that go along with it can give you a baseline of actually what kind of energy use intensity that building has. We'll get a little bit more into systems efficiencies later, but it's a way to set the parameters, and then after you go in, and this is hopefully what we'll get a shot to do 2 or 3 times here before the end of the semester, we'll get to go into a structure, we'll test it, we'll see what the air change per hour rate is, we'll do some energy improvements, and then we'll test it again. So hopefully we'll be able to make a marked difference in it, and even calculate how much energy is going to be saved through the improvements we do. The one thing about the blower door when it comes to systems efficiencies in existing houses, it starts to give you that checklist of what's going to be your low-hanging fruit, which ones are going to benefit the most from air sealing. So again, we're not measuring total pressure, just the difference between the pressure. So it's preference or with reference to one another, and we'll talk about this, and this will become common for you when we're talking about blower doors. But everything's measured in pascals, and it's a replacement of pounds per square inch measurement of pressure that usurped the imperial system, but there's a couple different comparisons of it here. 249 pascals is a standard 1-inch water column, and listed as a water column is the pressure required to suck 1/2 inch of water up a straw. And that should say, it says just over 1 pound per square foot. That's in reference to 50 pascals, and 50 pascals is the standard measure of what is usually set for blower door operation. But when you hear somebody talk about, again, the difference between natural air change per hour and air change per hour at pressure, they're always talking about that pressure at 50 pascals. So the basic concept of the blower door is it creates the pressure and then it measures how many cubic feet per minute of airflow is going through that fan. And I'll go back to that slide in a minute. So this is a basic blower door, very similar to the one that we have. It is just that. It's a fan in a door. It's the frame goes in the door and it gets sealed up all around. We have the pressure gauge so that we can measure the outside atmospheric pressure and then create the artificial 50 pascal situation so that we can actually run the test. Again, 50 pascals is pretty much the standard. And that's when you see things in that CFM 50, basically that's recording the cubic feet per minute at pressure that's entering or exiting the building. So this is what they look like. And we won't spend too much time on this. We'll actually get to use the real blower doors and see those. And there's an example of one from the outside that's in use, and you can't really see it on this picture. You can if you download it, but you can see that the fabric on the blower door is really pulled back in because it's working to create that pressure inside the house. So exhausting, creating negative pressure inside the house, so it's just sucking that back in. We're going to work with all of the automated gauges, so we don't have to worry about reading the MagnaHelic gauges anymore. There are still some blower doors floating around that have them, but yeah, they're pretty much dinosaurs. The way that they work, you're trying to set up the house in what's called winter mode, so closing all the windows, closing all the doors. You really want to seal up anything that's not in a natural state. Fireplace dampers, although to effectively do a blower door test, and some people do this, and you don't want to close dryer vents, things that are actually supposed to be part of that thermal envelope. Same thing with range hoods and air handlers. But you do want to close the fireplace damper, and yes, you do want to take ashes out of the fireplace because you're creating negative pressure, and if you have a leaky flue, it's going to come right down and blow all the ashes into the house. Couple other things, and we'll spend a little bit more time in this. You'll see with the blower door fan, it starts at about a 24-inch diameter fan, but it's got a series of rings that you can add to it. As we get the houses tighter and tighter and tighter, we don't necessarily need that much volume of air going out. You would create a situation where if you're running the fan without any of the rings and you're looking at a passive house or a very, very tight house, you will be creating a significant amount of negative pressure. In one house that we were working on years ago, the energy auditor came in and was running the blower door, and it was one of his first blower door tests, and he didn't realize how tight the house was. It ended up testing out just under 1 air change per hour at 50 pascals, but he didn't put the airflow rings in there to start, and so he had the house up to about 115 pascals in a hurry. So in an older house, a lot of times you will have CRF, which means you can't reach 50 pascals. If you get in a house that can't reach 50 pascals, you've got a lot of air sealing to do. So it just means that it's got so much air change in it that you can't get it to pressure. There's more air leaking in than you can possibly exhaust. But basic controller, we'll spend more time on this when we get them set up and we have our demos. And for the online folks, we've got some online demo stuff that they can go through. But the two main parts of it are the A channel, and that's keeping your pressure differentiation the same. And as I mentioned, with the blower door, you've got your external hose, and that's measuring your atmospheric pressure, and that's connected into your controller, so your controller actually does the work for you, and it keeps it at 50 pascals. With the older style blower doors and the MagnaHelic gauges, you had to constantly keep adjusting it, and it was pretty hard to keep it at 50 pascals consistently. And then the other channel is one that measures the airflow that's actually going through the blower door. So there's a little sensor in the door right at the fan, and that's what measures. There's a better picture of it there, right there. It's just a little flow sensor, and that's connected to your controller, and that's giving you your cubic feet per minute reading on that. These are a couple of the other, we talked about cubic feet per minute at 50, just some of the abbreviations and acronyms that you're going to need to remember and know. CFM natural, so that is your everyday air leakage. And the other thing that we'll talk about is the N factor. And so the N factor is one that's used to equalize and to try to determine what the natural air change is. It ranges from 9.8 to 29.4, and it depends on your type of construction. It depends on your climate zone. And I'll jump back to the slide in a minute. So here's just a chart of what the N factor is, and it's a little bit qualitative in some ways. You can see that it's broken out into 4 different zones across the U.S., and depending on what zone you're in, and depending on the number of stories of the building, and then that's the qualitative sort of, is it exposed, is it normal, or is it well shielded? Depending on where the building sits, you have to make that call to put in the N factor. Really all that's trying to do is if you have a building, if you've got a 3-story building that's sitting on the very top of a hill without a tree in 50 miles, it's probably going to have a higher N factor than a 1-story building that's tucked away right at the toe of a hill surrounded by trees. So it will make a difference in your natural airflow, and so that's why you put that N factor in there. It's just a way to try to equalize. It's hard to compare apples to apples on every single building, because building the same building and putting it in point A and point B, depending on how they're shielded, could make a difference in how it performs. So basically what you're trying to do is determine how much air is leaking through your house. And so, for example, if your N factor is 10, you're at 50 pascals and you're reading 5,000 cubic feet per minute, it could be the equivalent of a 500 square inch hole in your house. That's a lot of air leakage. I'm not sure you could get, you might get a CRF, can't reach 50 if you've got that much air leakage. So one of the things to, where's my slide? There we go. One of the things to work on as well too is you can't really get your air change rating until you know the volume of the house. For example, if you've got, so back to that 5,000 cubic feet per minute, if you've got 5,000 cubic feet per minute and that's in a house that's 10,000 square feet, that might not be all that bad, but if you've got 5,000 cubic feet per minute in a 1,200 square foot house, it's pretty awful. So before you can really make any sense of what reading you get out of the blower door, you have to be able to calculate the volume of the house. So back to the thermal envelope, you got to be able to locate the thermal envelope and then do your volume calculations. I would tell you this slide is a little older, so new houses are looking at air changes per hour at 50 of 5 to 10. Minimum code is 4 at this point for state of Montana. So new houses are, I would say, usually between 2 and 4 at this point. Older houses is 11 to 15, where it says up to 30. Yeah, some older houses that you'll go into, again, you can't even get pressure because their air change per hour is so significant. So converting back, to try to do that, this is a simple exercise, and this is part of, once we get into ResCheck next week and we start playing with that and we do our heat load calculations, these are some of the things that you'll have to do on a simple scale like this. So this house, for example, 40 feet long, 28 feet wide by 8 feet high. And we're assuming here in this building design that we're looking at a thermal envelope that's just flat across that 8-foot ceiling. So we're not looking at an attic design. So in order to, we calculate our dimension or our volume inside, 40 by 28 by 8, which is 8960. So we're at 8,960 cubic feet inside the house. We have a blower door reading of about 4,500 cubic feet per minute at 50 pascals. And so our air change per hour, in order to calculate what our air change per hour is, we take that cubic feet per minute reading, stop it. We take that cubic feet per minute reading times 60, because we're trying to get this at an air change per hour rating, and then we divide that by the volume of the house. So in this example here, we got a reading of 4,500 cubic feet per minute times 60, which, what is that, 270,000? Is that right? I didn't run the math on 4,500 times 60. 270. So you've got 270,000 divided by 8,960, which is the volume of the house, 40 by 28 by 8, and you come up with 30 air changes per hour. So it's a pretty darn leaky house. If we wanted to come up with, you can do this inversely as well to try to get a target. So let's say, for example, we were designing this house and we wanted it to test at 4 air changes per hour. You know your volume, you're at 8,960, right? So you'd have to come up with what your cubic feet per minute flow would be. Does that make sense? So let's say we were shooting for 4. We've got 8,960. So X 60. I don't have my calculator, but I'll try my phone. We're probably going to have to get to a reading of about 600 cubic feet per minute, if I'm doing that right in my head.
Yeah, to get to 4.
To get to 4.
Yeah. Yeah, that's correct. 600.
600? we don't have to get the exact number on it today. It's not
It gives you 4.017.
4.017? Yeah. So if you came into this situation, and this is say this is one of the houses we're going to do the weatherization on, we come in, we do the blower door test, we figured our volume, and we got our reading of 4,500 cubic feet per minute. Our target is 4 air changes per hour. Now we've got something to work with. Now we know we need to get down to 600 cubic feet per minute through the blower door. Does that make sense? Is all more math than you care to do at 3 o'clock in the afternoon?
And how easily you can get down to 400, based
Well,
on
that's kind of the rest of what we're going to talk
what
about.
the envelope looks like, if it's an easy fix or if it's a lot of little things.
And that's this is kind of the spot to end on that. That's kind of the next thing we're going to do, and we're going to play with the different building assemblies, and figure out not only which assemblies work better in new construction, but in existing construction, where are the weak points, where are we going to get the most bang for our buck in air sealing, and it's different on every house. Not every house is going to be the same. One of the things that's pretty interesting about doing the blower door tests and getting in and doing the weatherization is you get to play detective a little bit. You get to go in and find out. You may do one house. You could have these two houses sitting side by side. You could have these identical 40 by 28 by 8 houses sitting side by side, and you could get the same exact reading out of both houses. But one of them might have a condition where you've got no air sealing in the rim joist between the first and second floor, and no air sealing in the attic, and that's where 60% of your air leakage is coming from. And the other one might have windows and doors that don't have any air sealing. And so this is where the next thing we'll talk about. Once we start to get familiar with the blower door, we're going to use the thermal imagery camera, which is going to help us find those problem areas. So, does that stuff make sense? Is any questions on that? Basic blower door, how it works, the operation, how we measure? Have you heard those terms before?
How much does a blower door setup cost?
A good blower door is probably about $4,000. And the thermal imagery camera is going to be anywhere from $7,000 to $14,000. It's not an inexpensive profession to get into to start, but
But if you're improving somebody's house by like from 4,500 to down to 600, they're going to